Let's talk about non-homogeneous differential equations using the method called variation of parameters. Now, the non-homogeneous differential equation in its general form will be something like this: y double prime plus p of x multiplied by y prime plus q of x multiplied by y equals certain function called f of x. As we remember, in the homogeneous equations, this term is usually 0 and this term is almost identical. Now your general solution will be y equals y homogeneous, we represent it as y of h, plus y particular, which we represent it as y of p. Now you take these two parts, each one aside, so that you can simplify the process of the solution. So firstly, you take the homogeneous part of the solution. So we focus on yh, which is the homogeneous part of the equation. Then this one, as we know, should look like this form: y double prime plus p of x y prime plus q of x y equals to 0. Now we have, in this kind of equation, let's call it equation number 1, it's a regular homogeneous differential equation. You can solve it with any of the methods that we discussed before. Let's say we want to use the exponential guess method to solve this problem. Then we move forward to our particular solution. So the second part is the particular part. So your particular solution, y particular, should equal to u of x multiplied by y1 plus v of x multiplied by y2. We want to mention here that your homogeneous solution, the general solution, will have y1 multiplied by certain constant factor plus y2. That's where you identify your y1 and y2 in your particular solution. Now we can see we have u. Now you have an equation. So u of x equals minus the integration of y2 multiplied by the right hand term of the main equation, f of x, divided by w, which represent the Wronskian factor. And we will write on the side, so the Wronskian factor equals y1 as in the determinant and y2. Then we have down here y1 prime, and we have here y2 prime. Then by solving this determinant, you can get your Wronskian value that you can plug it back in the equation here. Of course, this is an integration in terms of dx, and you have your v of x. Now the v of x equal the integration of y1 multiplied by f of x over the Wronskian value in terms of dx. Okay, so when you have your particular solution, you plug it back in the equation. You have your homogeneous solution, you plug it back in the equation. then you will have the general solution for the problem that you're trying to solve. Okay, now trying to move for an example that will clarify what we just discussed. Let's take an example. Let's say we have y double prime plus 4y equals secant of x. So this is a non-homogeneous differential equation. We can solve it using the variation of parameters method. Firstly, as we said, the general solution will be y equal the y homogeneous and y particular. Let's start with the homogeneous part. So in order to find y homogeneous, we want to write the homogeneous equation. So this is equation number 1. The homogeneous equation for equation number 1 can be y double prime plus 4 multiplied by y equal to 0. We just zeroed out the right hand side of the equation. Now we have a homogeneous form of equation. We can use the exponential guess method. Any method that works for the homogeneous equations can be used here. In this particular example, we can use the exponential guess method. So using that method, we can represent the equation number 2 in terms of lambda, as we discussed before. So it can be lambda squared plus 4 equals 0. From that, we can find the value of lambda 1 and lambda 2, which happens to be plus or minus 2 multiplied by I. It's complex roots in this case. So now we can say that from this, y1 equals to cosine beta of x, which is cosine 2 of x, and y2 equals sine beta of x, which in this case sine 2 of x, and the y homogeneous equals c1 cosine 2 of x plus c2 as a constant multiplied by sine 2 of x. So this is the homogeneous solution. We want to keep it in mind. So we solved half of the problem for now. What's left is to find the particular part of the equation. Okay. Moving forward, in order to find the particular part, so yp, as we said, equals u of x multiplied by y1, we already have y1, plus v of x multiplied by y2, we already have y1 and y2, but we want to find u of x and v of x. So moving forward, as we mentioned earlier, u of x is the minus of the integration of y2 f of x. y2 in this case is sine 2 of x. f of x is secant of x over the Wronskian. Let's try to find the Wronskian on the side. So the Wronskian equals the determinant of y1, which is cosine 2 of x, and y2 sine 2 of x, and y1 prime, which is happened to be minus 2 sine 2 of x, and y2 prime, which is 2 cosine 2 of x. Solving for this determinant will give us a value of 2. Now let's compensate that in here. So over the Wronskian to be integrated with respect to dx, this will give you the value of ux to be equal to cosine of x. V of x is the integration of y1, which is cosine 2x, multiplied by f of x, which is secant x, over Wronskian, which is happen to be the value of 2, integrated to with respect of dx. So this can be cosine 2x secant x over 2 d of x. That will give you sine of x minus 1 over 2 ln of secant of x plus tan of x. Okay, so in here we found our u of x, we found our v of x, we already have y1 from the homogeneous part, and we have y2. Now we can find the particular solution for this equation, which happens to be y particular equals u of x is cosine of x multiplied by y1, which is cosine 2 of x, plus v of x, which is sine x minus 1 over 2 ln secant of x plus tan of x multiplied, let's put these in parentheses, multiplied by y2, which is sine 2 of x. Okay, now the grand solution for this equation will be, we said previously, it is a combination of the homogeneous part of the solution and the particular part of the solution. Homogeneous part happen to be equal to cosine, let's say here c1 cosine 2 of x plus c2 sine 2 of x. Let's put them in parentheses as a homogeneous part, plus the y particular, which is the long solution mentioned over here. It is cosine x multiplied by cosine 2 of x, put in parentheses, plus sine 2 of x multiplied by sine of x minus 1 over 2 ln secant of x plus tan of x in parentheses, and this is the particular part of the solution for this equation, and this is the grand solution for our problem that is mentioned earlier.